HVAC 360, episode number 48. HVAC Refrigerants. All right, and welcome back, everybody, to another episode of HVAC 360. I'm your host, Matt Nelson. This week, we're going to be talking with a professor over at Purdue University, Dr. Eckhard Groll. We're going to be talking about HVAC refrigerants. This is always some good information to have in your back pocket. You may not necessarily use it every day, but it's good to have a good knowledge base about refrigerants and how you should use them in design, how you should advise clients, things like that. So we'll go right to the tape with our interview with Dr. Groll. All right, this week we're talking with Dr. Eckhard Groll. He is a professor of mechanical engineering at Purdue University. How are you doing today, Professor?
I'm doing just fine.
Great. Hey, now, can you tell me a little bit about your background in mechanical engineering and kind of, where you came from?
Sure. I got actually educated in Germany. I got a diploma in mechanical engineering from the Ruhr University of Bochum and a PhD from the University of Hanover. But I spent time towards both degrees in the U.S. I spent a year at Texas A&M towards my diploma, and then I spent some time at University of Maryland to do PhD research and stayed in Maryland as a postdoc before I came to Purdue in 1994 as an assistant professor. So I've been at Purdue now 18 years this summer, and I moved up the ranks from assistant to associate professor, and since 2005 I'm a full professor.
Excellent. Now, you also are a director of a cooperative education, is that?
That is correct. I'm the director of the Office of Professional Practice, and we direct all of Purdue's cooperative education programs. We have about 600 students in various programs through that office.
Now, does Purdue offer a architectural engineering program, or is it just strictly mechanical?
No, we do offer an architectural engineering, we call it area or a subsection, or so it's housed within the School of Civil Engineering. So it's not, the students still get a degree of a Bachelor of Science in Civil Engineering, but they have a specification, if you want to, a topic area of architectural engineering.
Interesting. Now, so I guess today we're going to be talking about HVAC refrigerants. How did you get into refrigerants?
How I personally got into refrigerant was I finished my diploma in Germany at the end of 1989, and I had a specialization in heat transfer, thermodynamics, and fluid mechanics, more so the thermal sciences, basically. And I was shopping around for a PhD position, and at that point, everybody was talking about ozone depletion and phasing out of the classical refrigerants, if you want to name them that, and finding alternatives and solutions. There was lots of research funding available to look at alternate refrigerants, and I found the topic very interesting from what I picked up from the news at that point. And so I was offered a position at the University of Hanover to look at an alternate technology, including alternate refrigerants to be used for the common vapor compression refrigerants.
Now, I think the one thing that interests me about refrigerants is kind of the naming of them, because the naming of the refrigerants, whether it be R11 or R132 or R410A, those have specific they're almost like model numbers. They kind of tell you exactly what those components are made of. Can you kind of tell me a little bit about the chemistry behind the naming standpoint, or how do you decipher them?
Yeah, that's a very interesting question. I love to talk about this. I can give you first. We can start out saying what it actually means. If you have a refrigerant, let's say 134A, the first number, the 1, stands for how many carbon atoms are in the molecule minus 1. So 134A actually has 2 carbon atoms in the molecule. You subtract 1, and so you have a 1 there at the first number. The second number is a 3, and that is the number of the hydrogen atoms in the molecule plus 1. So there are 2 hydrogen atoms in the molecule, and you add 1, that makes a 3. And then the 4 is the remaining bounds of the molecule are filled up with fluorine atoms, and so you have 4 fluorine atoms that make up the molecule now. So that sounds actually complicated, and the reason why it is so complicated is because the person who invented the classical CFC refrigerants was Tom Midgley, and he initially didn't want anybody to know what he was working on. So he invented a number scheme that is actually kind of confusing, that is kind of misleading. And but because then everybody eventually picked up his refrigerants that he invented in the 1930s, we're still sticking with his numbering scheme today, even though it was invented to confuse people or his competitors not to know what he was doing, and we're still doing it today. So it's absolutely fascinating.
Now, so I mean, obviously with the 3-digit numbers, what if you went down to like the R11, the R22? What? So
the R11 or R12 means there's a 0 in front that is actually skipped. So the real number scheme would be R011 for R11 and R012 for R12, which means they only have 1 carbon atoms, but we're subtracting 1, so there would be a 0 in front. The 0 is typically skipped, but there is actually an official nomenclature, there would be a 0 in front.
Interesting.
And the A in 134A, I forgot to mention that. The A means it's an asymmetrical atom. So if you have, for example, the 2 carbons, 4 fluoride, and 2 hydrogen, you can put the 2 hydrogen on one side of the molecule, and then it's asymmetrical, or you can put 1 hydrogen on each side of the C atoms, and then it's a symmetrical molecule, and so then you have actually the refrigerant R134, which does exist but doesn't have any commercial value.
Yeah, that's fascinating. Now, I guess the one thing that I know, what about like 410A? I mean, having a 4 in there, is there like, because I remember like, an azeotrope or an isotrope.
Yes, so we're using this definition of refrigerant numbers like the 012, for example, for R12, and then the R134A, and then we have R245F, FA, for example, to indicate the molecule structure with the F and the A. But beyond that, we're deviating now from this number scheme. You can already imagine with R2XX series, you have now 3 carbon atoms, which make the molecule very large. And so while you could create larger molecules, they're not very commercially viable anymore. You don't have the thermodynamic characteristics to really do well in a system. The transport properties are not so good. So it was decided by ASHRAE actually to use 400 series, so 4XX, for mixtures, as well as the 500 series for mixtures of when we start mixing 2 or 3 refrigerants together to create a new fluid. And the difference between the 400 and the 500 series refrigerants is the 400 have what's called a temperature glide, which meaning during a constant pressure evaporation or condensation process, the temperature does not stay constant. They actually, the temperature has a certain range, a certain temperature difference from the start of evaporation until the end of evaporation at constant pressure. And we call that a temperature glide. while the 500 series refrigerants create an azeotrope, which means they actually at a certain concentration have just one saturation temperature that goes along with the pressure of the system during the evaporation, the condensation process. And so they kind of, even though they're mixtures of multiple refrigerant, they behave like a single component refrigerant, and that's the 500 series designation.
Wow. Yeah, because I know that the one thing, at least from a practical standpoint, is that if you had, R11, R12, versus R410A in a system where, if there was a leak in an R12 system, you could just end up adding more R12 and you'd be fine. Whereas if you had, 410A, you really had to take everything out and put a whole new mixture back in, because it is that combination that multiple different refrigerants being put together.
Yes, that is correct, and the reason is, in fact, exactly this temperature glide that I mentioned. So if you have one constant pressure in the evaporator or the condenser, the liquid phase and the vapor phase have slightly different compositions. How different will depend on the refrigerant mixtures and the difference in this temperature glide that you experience during the condensation or evaporation process. And so now if you predominantly leak out the liquid phase, you leak out one refrigerant more than the others. If you predominantly leak out a vapor phase, you get the other refrigerant more leaking out than. And so you're with the leak in the heat exchanger, and only in the heat exchanger, though, you do create a concentration imbalance, and that's why you would need to take the complete charge out and recharge it with new refrigerant to maintain the concentration that is accurate. But if the leak is anywhere in the vapor phase or in the subcooled liquid phase, right, like in the liquid line or around the compressor, then you don't have to do it, because there the mixture is homogeneous again. This phenomenon really only occurs in the heat exchanger and would only occur if you have a leak in the heat exchanger.
Excellent. Learn something new every day. So now the refrigerants themselves, when you talk about refrigerants and you talk about the different protocols that have been issued about them, they all have kind of different kind of, I guess, characteristics that, aside from their names, they're going to have different global warming potential and ozone depletion. Can you talk about the different characteristics that the refrigerants are classified by?
Yes, sure. I mean, you can certainly classify ozone depletion potential, which is everything is related to R11 as one of the refrigerants with the highest global warming potential. Ozone depletion potential, and what it indicates is to what extent does this refrigerant, if released to the atmosphere, and when the molecule breaks down, deplete the ozone layer. That is a relatively chemical complex process that happens in the stratosphere as certain ultraviolet radiation hit the molecule. It breaks off the chloride, and the chloride reacts with the ozone and breaks down the ozone layer. So that is strictly a phenomenon of the chloride being in the molecule. And so if the molecule has a lot of chloride, then typically the ozone depletion potential is high. And so a decision was made over the years to phase out all CFC refrigerants, which means the chlorofluorocarbons, which had a very high amount of chloride and no hydrogen on the molecule, just fluoride and chloride. That was therefore phased out in '96, and then now in 2010 we even phased out the HCFC, which are the hydrochlorofluorocarbons, which have hydrogen in addition to the chloride. They're not their ozone depletion potential is not as bad but it's still significant enough that we had to phase them out. And so out of the new equipment that phased out in 2010 and out of production, they will phase out in 2020. So we still can recharge system but not use them. But that is just one aspect. A different aspect that you mentioned was the global warming potential, which is how much do these refrigerants contribute towards the global warming phenomena, which is basically closing out windows for us as the Earth to radiate towards the universe, and so radiation is reflected by these gases in the atmosphere to come back to Earth, therefore heating up our atmosphere. We cannot radiate out to the universe. They're closing certain wavelength windows. That is everything there is related to CO2 as one of the primary gases that has this effect. But the big difference is in CO2 we are exhausting in millions of tons during fossil fuel combustions. Refrigerants we are releasing through leakage and other things in systems to the atmosphere. But the global warming potential of refrigerant is much higher, in the order of 1,000 times of that of CO2 for an equal amount of mass. And so there's still a big concern about this, and we still have to worry about it. In this case, though, all of the refrigerants, irregardless if they were the CFCs or the HFCs, and now the replacement, that the ones that we currently use, it's the HFCs, which don't contain any chloride anymore, just hydrofluorocarbons. So they have zero ozone depletion, that's good, but they still have a significantly high global warming potential, where we still have to think about alternates or contain these refrigerants better as they contribute to global warming.
Now, there are out there some more, or I should say less common refrigerants out there that are not in the same category. How are those classified?
Yeah, so that's a very, very good question. So the refrigerants that you're probably referring to are typically called natural refrigerants. That is just a name that certain aspects of the industry gave them. The idea is these are refrigerants that are naturally occurring in the biosphere. So substances that we have in the biosphere already, as compared to chemically manufactured refrigerants. Typically, those refrigerants are classified by the letter by the 700 series. And their molecular weight. Classical example is, for example, CO2 can be used as a refrigerant, is naturally occurring, and it's 744. So 700 series and then 44 for the molecular weight of CO2. Ammonia is another substance that is naturally occurring, and so ammonia is 718, right? For NH3, so nitrogen and 3 hydrogens is 18, and then we have some others. The hydrocarbons, which also considered natural refrigerants, so hydrocarbons like propane and methane or butane. Sometimes they're not necessarily really naturally existing as just a pure substance, but in many cases they are naturally occurring, for example, in what we call natural gas, as a mixture of these substances. They do naturally occur. They actually go back to the R designation that I just mentioned to you. Propane is, for example, R290. So that follows exactly the scheme that I just mentioned. It has 3 carbon atoms and then 8 hydrogen atoms to fill the 3 carbon atoms. And so that's the 9 and then 0 of fluoride or chloride. Or so that's how you get up with R290.
Excellent. So I guess when we're, and I obviously I would think that since they have more of a, traditional naming system, that, these are, since they were available, that's, typically what people might have, started, trying to use the refrigerants, trying to use them back when they were first started to be used. When did the use of refrigerants come into play?
And really with the Industrial Revolution in the mid-1800s. And this is when people started building the first, we started out building steam engines, but then very quickly people realized you can reverse the cycle and do a refrigeration cycle, which is really a vapor compression refrigeration cycle. Is just a reversal of a Rankine power cycle, which is the classical steam engine cycle. So mid 1800s, the first patents go down to 1834 and then 1850 for the first compressors. And the refrigerants that were used at that point were substances that were available at that time. And so available was ammonia. Ammonia was one of the very early refrigerants used. Available were also a lot of ethers that were used in the printing industry at that point as cleaning substances and stuff. And they can be used as refrigerants too. And all of them had, of course, some major concerns, either like toxicity or acidity. They were corrosive. They were aggressive. So it's challenging substances, but those were the early substances that were used in the 1800s, and then at the end of the 1800s, around 1900s, we started using CO2 quite heavily. That was a refrigerant of choice. It's a high pressure refrigerant, also not without challenges, but it's not doesn't have the toxicity, doesn't have the aggressivity or corrosivity that some of the other substances had. Very interesting, but nothing was really satisfying to the industry until Tom Midgley in the 1930s created the CFCs, the R11, R12, and they were immediately considered miracle substances. They had all of the stuff that people wanted as a refrigerant. They were like safe in handling, they were easy to use, had low pressures, they were ideal to mix with mineral oils for the lubrication of the machinery of the compressors and stuff. So they took over like a flash in the entire industry very quickly. But that didn't happen until the mid-1930s. Up until then, we used all these different, sometimes today called more exotic substances.
Now, so it came into the industry, the R11, R12, and they're really they're great. Did they? I mean, as far as comparing them to the performance of the refrigerants that we have today, were they so much better? I mean, are we getting rid of efficiency for the sake of the environment? Is that the trade-off that we're having?
So before we go into that discussion, let me tell you, I find this phenomena really absolutely fascinating, because there was a substance invented in 1930, right, and it was literally hailed as a miracle substance. If you go into the literature at that point, everybody loved this. And 40 years later, I mean, literally in the mid-1970s, we discovered these substances that were considered absolutely like fascinating, the best thing that we could do, actually do tremendous havoc to our environment by depleting the ozone layer, which is like a very big issues for us as living beings. So absolutely mind-boggling, right? That something that was so convincing and so great could have such a detrimental impact so many years later until we discovered it. So now we replace these ozone depleting with HFCs. You asked about efficiencies. The efficiency is still as good or maybe even better than with the CFC refrigerants because the technology still advances. If the fluid may be a little bit less efficient, we are building much better compressors, much better heat exchangers today. We're doing much better on the process. So overall efficiency of our equipment with the switch over from the CFCs and HCFCs to the HFCs that we currently use is still just fine. We still actually improved efficiency of equipment. So we're not lagging behind, or we're not making any mistake towards the environment. The bigger challenge is the current challenge. We still realize that these replacement refrigerants have a significant global warming potential. We would like to get rid of that as well. And so if we get rid of the HFCs, what is next? And where we go from here? And so that's where I think more the question that you just asked comes into place, because if we now go back to the naturally occurring substances and put them into systems, then people are concerned that we cannot meet the efficiency criteria anymore. And so we may be good for the environment of the direct refrigerant not being released to the atmosphere anymore, we may be indirectly bad because we're consuming more energy to run our equipment. That would not be acceptable, I think, to anybody. So even with this next phase of switch over or whatever we decide to do, we still need to provide equipment, overall systems that are more efficient than what we're currently doing. We cannot lose the efficiency again.
Mm-hmm. Now, obviously, you've kind of mentioned the phase-outs. Can you kind of recap exactly, if somebody didn't know anything about refrigerants or what's been going on or why they did away with R11, R12, what have been the major pieces, globally speaking, because these are global kind of, protocols that have going on.
Yeah, we have two significant protocols. The first protocol was the Montreal Protocol that started in 1976 that regulated the ozone depleting substances. They were subsequently amended a couple times to the point where any CFC, as I mentioned, so these are the chlorofluorocarbons, the refrigerants that have high ozone depletion potential, had to be phased out in 1996. They were completely gone from the market at that point in 1996. And they were, in most applications, replaced directly with HFCs. These are the hydrofluorocarbons. They don't contain any chloride anymore and therefore have zero ozone depletion potential. But in some applications, they were also replaced intermittently with HCFCs. So these are the hydrochlorofluorocarbons. They still contain a little bit of chloride and have a small ozone depletion potential. And governments gave us a little bit more time to phase them out. So in new equipment, they're phased out in 2010. So you can't get any new equipment anymore on the U.S. market that contains any chloride refrigerants. That's completely gone since 2010. And any new equipment now will have just HFC refrigerants, so no more chloride and zero ozone depletion potential. But we can still use these intermittent refrigerants, the HCFCs, until in existing equipment to recharge existing equipment, and we can do that until 2020. So we still have a little bit of a grace period there before that refrigerant is completely gone, or even in existing equipment. Does that answer your question?
It does. And how do you, now you mentioned the Montreal Protocol, which is probably the biggest and well known. What about the Kyoto Protocol?
So the Kyoto Protocol now addresses the global warming, right? And that is the second aspect, and that has also been started to being amended. And so the idea here is that even these HFCs that we currently then using as replacement and that we currently selling in new equipment and or converting existing equipment over to these, that they have a high global warming potential, and as they release to the atmosphere, they contribute significantly to global warming, and so we need to either get rid of them, that will be one approach, or at least do a better job containing them. But containing is easier said than done. I give you the classical example that I give my students in class is automotive engineering, right? We have in the U.S. about 200 million cars on the road. Typically, they all have air conditioning. And the typical charge in an automotive air conditioner is 2 pounds of R134A. So now you have 200 million cars times 2 pounds, so you have 400 million pounds of 134A on the road in the U.S. at this point. Studies have shown that automotive air conditioning is one of the highest leaking systems. And the reason is you have an open drive compressor. That means the shaft of the compressor comes out of the shell and is driven by a pulley via the engine. In addition, the whole system is connected to the engine, which is exposed to high vibrations. So you have flexible hoses to limit the impact of the vibration on the system, on the firm system components. And so you have a lot of connections, you have flexible hosing, you have an open drive compressor shaft seal. All of this means, irregardless what we're doing, we cannot get that system to 0% leakage. It's just physically, technology not possible. So an automotive air conditioning system will always leak. We can minimize the leak, but studies have shown that actually a car loses about half of its charge over 2 years. So now let's go back. I said we had 400 million pounds of 134A in cars. Half of that, right, 200 million pounds over 2 years. That means we're leaking 100 million pounds of R134A every year into our atmosphere, and this is the U.S. alone. So that is tremendous, right? That is an application where we absolutely have to use a different refrigerant, right? That 134A has a high global warming potential. The impact is huge. We got to get rid of it and use a different refrigerant.
Wow, that is significant. Now, I guess when we talk about the refrigerants being used today, obviously there are some winners in being developed. What are some of the and I know that if you look at like compressors for like refrigerators, and it seems like different markets have standardized around different types of refrigerants. Do you have any feeling for that?
Yeah, I mean refrigerants by its nature have a certain thermodynamic characteristics and performance. And so some refrigerants are good for certain applications, while other refrigerants are good for other applications, right? So the automotive air conditioning used R12 and then was phased over to 134A, and we need a refrigerant that has somewhat similar performance when used in that type of system. And the main characteristics here is like at what temperature do we evaporate the refrigerant and get the cooling effect into the passenger compartment versus at what temperature are we rejecting the heat in the front of the engine compartment. If you go into a residential air conditioner, that will see very different, maybe not super different, but somewhat different operating temperatures. And if you go into a supermarket system, which needs to provide freezing of frozen pizza, frozen veggies, and ice cream in their display cases, that yet uses a completely different operating temperature for their system. So for each of these systems, we have traditionally specific refrigerants that give us optimum performance. Classically, we're talking about maybe 5 different refrigerants that could cover most of the market, right? So we had in the past when we started out, we had about R12, which used household refrigerator, air conditioning. We had R22, which was used for any type of residential air conditioning, including commercial air conditioning and medium temperature commercial refrigeration. And then we had R502, which was the commercial refrigeration at low temperature, the supermarket low temperature that I mentioned. Then we had R11 for the large air conditioning, for the like centrifugal chillers that are used for large office structures or airports or hospitals. Or so. And then we also always used ammonia to some extent for industrial refrigeration, like breweries or refrigerated warehouses, where you're not in contact with just the general population, where only mechanics are in contact with the system. So all of these are gone. Like R12 was replaced with 134A, 22 was replaced with 410A, 502 was replaced with two refrigerants, 507 or 404A. They both have market share, and R11 was replaced with R245FA. So they are all, but all of these are now HFC refrigerants, and all of these are still under scrutiny, as we discussed.
Now, what do you tell? I mean, obviously, when you're dealing with building owners that have an existing equipment, and they have some antiquated equipment that may be 30, 40 years old, what are your options, as far as what to do with some of the equipment?
So if it's 30 years old and it's still operational, get rid of it right away. So I mean. Actually, most systems, really the longest lasting systems, are usually certified for 20 years. So like your residential air conditioner or your residential refrigerator, freezer, they usually maintain performance and are good up to 20 years. Once you hit 20 years, I would automatically replace them anyhow. But more critical is like what is with the equipment that is maybe 10 years old. It still uses the old refrigerant. It still performs reasonably well, but we're not using this refrigerant now anymore. And so in those cases, you really have to make a decision how environmental conscious you want to be. If you're in need of recharging, if you start having a leak of the system and you know it, and you need to annually put more refrigerant in to maintain performance, I would always recommend to replace it because the environmental concern is too great. If the system is still leak tight, you don't have to recharge. You're just operating it. You can wait until you get close to the 20 years and then replace with new equipment. So those would be my recommendations.
All right. So now, I guess what sort of time frames for some of the existing refrigerants should we be up on?
So the real question will be is how long can we use the current HFC refrigerants, 134A and R410A, for example, as some of the very prominent two refrigerants in our existing and new equipment. And that's a question that you and I can gamble on, but we will not know for sure. And the other thing that comes into place now is politics and different regions of the world. Right, so Europe, for example, have made a commitment to naturally occurring substances as refrigerants. And so in Switzerland, for example, already 50% of their heat pumps, residential heat pumps, are running on propane, which is an excellent refrigerant. You don't have any problems with efficiency. You actually may even have an efficiency gain. But you have the high risk of flammability or even explosion if the propane leaks and it gets close to a flammable source. The U.S., with the current liability laws, has not adapted this technology, and there's a question if they ever will, or if they will, when they will. Very tricky discussion, right? But it's not necessarily a technology problem. I firmly believe that we can build hydrocarbon systems that are safe and reliable, but it is a problem of the laws of the land, and that means our liability laws are such that if an accident does happen, we have no upper restriction of how much money people can sue. And so, if there's a loss of life or something, companies that build this equipment could be sued for much larger amounts of money than in Europe. Europe has an upper limit on law cases like this, and so companies can build this into the overall profit margin much easier than in the U.S. So it's really, you get into all kinds of different discussions now, right? That are difficult to predict. So. But Europe, like I said, use propane for residential heat pumping. They use CO2 quite heavily for supermarket refrigeration systems. We are still not there yet, and not really that interested in that yet. There's other things that pull into this direction. We have most refrigerants are manufactured in the U.S. The biggest refrigerant manufacturers are DuPont and Honeywell, who bought Allied Signal, and Allied Signal traditionally was the next biggest next to DuPont. This is a huge market. I mean, as I mentioned, right? These companies have to produce 100 million pounds of R134A just to replace the automotive sector. Right? That means they're making a lot of money of this. You sell a pound of 134A for $12, $10 maybe on the market, right? So take that times 100 million. There's a lot of money to be made. They don't want to lose this market either, right? So there are forces at place that impact how this all shapes up and what refrigerants we may use in the future. Makes it very difficult to predict.
Yeah, and I can only imagine, especially if you just focus on refrigerants for cars. If you would take, say, a developing market like China, that there's so many more cars being put on the road there that have the exact same issue because they're no better than what everybody else is driving around.
Sure.
So
that makes that's exactly right, and I mean, and you can argue the point of the companies too, right? I mean, you argue, well, if we lose this income, right, as a chemical or refrigerant producing company, right, we're losing jobs, we're losing economy, right? That has a significant impact on our economy, and that's a decision that has to come into place too. But on the other hand, if we're convinced we want to maintain the Earth as a place to continue to live, comfortably, we may take the hit in the economy, right? To the better of the environment. I don't know. A very, very difficult discussion, but that is exactly the discussion that they do at the Kyoto Protocol and the other and the amendment conferences that are being discussed. Right. What's a reasonable way forward? Now,
as you kind of describe a lot of the different solutions that other European countries are coming up with, it seems to be that they're going back to the more natural type of refrigerants. They're not, we're not going back to, well, let's make a different molecule. Let's come up with a better refrigerant. Is there any of that? Coming into play?
Yes, that's exactly coming into play. We haven't talked about that yet, but DuPont and Honeywell have created yet another molecule. It is a brand new substance. They call it an HFO. Let me see. It's the O stands for olefins, I think, either hydrofluoroolefins. It's now has a designation of 1,000 series, and so they don't want to lose the market. They see the pressure on the HFC refrigerants, and so they're creating yet a new substance. The question with any of this is, can we say today what these HFOs will do in 40 years from now? That is, as a human, that is my only concern with going and chemically manufacturing new refrigerants, right? Because we can go back to the 1930s. At that point, somebody invented new refrigerants. They were hailed as great, and 40 years later, we found out they do something else. Do we create a new situation like this? So that's why certain entities and like Greenpeace, like others, say, let's go back to the 1800s. We had some original substances. These were substances that were naturally occurring and that we knew of, and they were used. We're going to use them again. We know what they do. They're very well investigated. We know the impact on the environment. We just need to make the equipment efficient enough to be competitive, but let's use those. While others say, well, but if we can produce new chemically manufactured refrigerants that have the same characteristics of the current ones that we can just drop in, substitute in, it's so much easier for the industry to adopt than just to switch over to completely different technology. And that is yet another discussion that feeds into the overall discussion. That is correct.
Well, I mean, and if you take a look at the refrigerants, the natural occurring refrigerants, say for example the carbon dioxide, that has the zero ozone depletion because it's an hemichloride, right?
Yes.
But it does have a global warming potential, doesn't it?
That's a very good question. Actually, CO2 as a refrigerant does not have a global warming potential. Not many people understand that right away. But the point is, we are not producing any CO2 as a refrigerant. Actually, the CO2 that we would use in refrigeration system is already existing CO2. We're not creating new ones. You could even say we could just use some of the CO2 that we create during fossil fuel combustion or other places and just store it for a while in a refrigeration system. But we would not create new refrigerants. So that's why that global warming potential in that case is, as a refrigerant, is negligible.
Okay. So and I guess what I was kind of trying to drive at, especially maybe with, I don't know if ammonia or methane, but are all the naturally occurring elements so squeaky clean that you couldn't produce a chemical refrigerant that would be just as good or not better as far as these two benchmarks go?
That's a good question, and I'm not certain. I wouldn't. I'm not that much of a chemical expert. That I know how to use them and I know the basics, but I'm not necessarily a person that creates fluids out of a molecule. I don't know. If that would be feasible or not. But I can say that hydrocarbons have a negligible global warming. So does ammonia, right? So that's that they all check out. They all have zero ozone depletion and pretty much negligible global warming potential. So, but they have other issues, right? I mean, hydrocarbons are flammable or explosive. Ammonia is toxic. Right? CO2, very high pressure. So they have technology challenges that need to be addressed on a system level. Now, could we create new chemical substances that have some of those properties, but not these detrimental, otherwise detrimental characteristics? Like I said, I'm not certain. Certainly, maybe if you believe some of the press from DuPont and Honeywell, some of these new HFOs will be such substances, right? They have very, very low global warming potential, zero ozone depletion potential, and should be safe to use and no toxicity and so on. Also, they are what they call mildly flammable. So they couldn't get away to make it completely non-flammable, but to ignite them is very, very difficult. But if you have the right mixture and the right source, ignition source, you can burn them, but with very low energy.
Mm-hmm. Okay. Now, I guess kind of just bringing it back around, now that we've kind of talked about all these CFCs, or these refrigerants, rather, as a designer, as an engineer designing new systems, are we just going to, try to pick the most current refrigerant and just, hope that it's okay? Or, I mean, obviously some of these, in-betweens are going to run out in like 2020, as you said.
So I'm as a designer. That's one aspect. As a researcher, let's talk first. I'm a researcher and I investigate new technology. So right now I'm doing quite a bit of work on making some of the systems that use these naturally occurring substances as efficient as current systems and as safe as current systems. So we're looking at how can we use the hydrocarbon in a residential system and be very safe with this, right? Have no risk of flammability or explosion or so. So that's a significant part of my research. But there is still a significant part of my research that still focuses on using the currently used HFC refrigerants like R410A and making those systems more efficient as well, and doing a better job with these refrigerants too, containing them better. So that we're still running in both directions, right? We still have to consider what we're currently doing, but we also need to consider looking into the future, what's going to happen afterwards.
Okay.
Right, and I think that as a designer in a company, if you work like in this industry, you would do similar things. You would look at we have current systems out there. We want to improve them. We want to make them better. We want to be competitive, but we also need to look into the future. What happens in 5 years or 10 years from now? What are the substances that we are going to use then, and what are the systems look like that we build then, and have some of your engineers focus on those aspects as well.
Okay. So I guess, regardless, stuff if we have that thought process to be diligent and looking at what's available, what's the most current, what are some of the alternatives, and making choices based on that, by the end of the life of the equipment, you're going to end up with a different set of rules and refrigerants, essentially, at that point in time anyway.
Yeah. No, and I agree with that. Actually, my vision really is that we see much more individualized systems for individual applications than we have seen in the past. There's not like one refrigerant that fits all, and it's really application by application. Like, for example, your domestic refrigerator freezer. Right, these systems are really considered leak-free for life. They're completely manufactured in a factory. The system is all soldered together. There are no flexible connections. There are no thread connections. It's all soldered together. You can manufacture a refrigerator that is leak-free for 20 years, and if you have a great recycle programs where the refrigerator comes back to the manufacturing site, you really don't have to worry what refrigerants you're going to put in, right? So there to continue to use an HFC is perfectly fine, right? As long as we recycle the refrigerator appropriately at the end of their life, we will never have a problem. The same is not true, as I mentioned, for the automotive application. So we're really looking at each application individually and seeing what is the best solution for that application.
Excellent. Fantastic. So now, I guess, if somebody wanted to learn more about refrigerants, what are some of the best ways to go about doing that?
So I currently serve on the board of directors of the American Society for Heating, Refrigeration, and Air Conditioning Engineers. This is ASHRAE. ASHRAE has a winter conference that happens typically in the last week of January, and an annual conference which happens to be at the last week of June. We just had our annual conference in San Antonio, Texas at the end of June a couple of weeks ago. And so going to ASHRAE website and looking what's available through ASHRAE is an ideal step to get more information. We have handbooks, we have position documents, we have standards of how to test and rate equipment. We have all kinds, and then of course we have technical publications that come out of these conferences. So we have all kinds of information available. We have short courses that we offer as part of our conferences to learn about the topic, the subject, and it's the website is just h3-048, and you find a lot of useful information there.
Excellent. Any last thoughts that you have?
No, I enjoyed the discussion. I'm glad I was able to talk a little bit about refrigerants. I can get very excited about the topic. I love the topic. It's a very research active topic, although not too many universities work in this area, but the universities that are committed to it are working very hard to find the solutions for the future.
Excellent. Well, I appreciate, Dr. Groll, you taking the time out of your busy schedule to sit down and talk with us.
You're very welcome.
All right, and we're back. Special thanks to Dr. Groll for taking his time to talk with us about refrigerants. It's obviously something he loves to talk about, and I think that shows through. Realistically, when you're comparing refrigerants and you're talking about the pluses and minuses of using some things that tend to be a little bit more flammable, like the methane or the propane, like he was referring to. And I can't help but think about my own house. Would I object to a propane compressor, propane refrigerant in my air conditioning unit? And I got to tell you, that to me, it's not a big issue. I mean, you think about it. My air conditioning unit sits right next to my hot water tank. Now, that could leak natural gas, just the same, and especially, the natural gas line runs throughout the house. How many points of does that leak? So when you compare the dangers and the issues about leaks, in conjunction with other things, that has to be put into play. I mean, on the other hand, if you had a heat pump that was in a in a classroom, would I feel safe about that? There it maybe gets a little bit different. But again, you have to like the professor said, you really have to take the application by application basis, and I think you're going to see a little bit more diversity. Whether it be different, if you have a mechanical system that's kind of sequestered between the mechanical room and outside area, maybe that can accept a wide range of refrigerant options, whereas maybe more centrally based heat pumps and things like that have a different agenda. So, but there again, carbon dioxide, why not in some certain instances? Anyway, great discussion. I hope you learned something from it, gave you a little bit of a perspective on refrigerants. I know that if you've never listened to a discussion on refrigerants, I think this is probably as good, if not better, than any of the others that I've listened to. So I appreciate Dr. Groll, taking the time to explain it and very succinctly. So. All right. If you have any comments, if you liked the discussion, if you didn't like the discussion, you can always email me at matt@buildingx.co, or you can follow me on Twitter at buildingx, or connect with me on LinkedIn. Either that or sign up for the newsletter at buildingx.co right there, and get the updates, some of the inside scoop, some things that the happenings around the HVAC 360 world. So until next time, I hope you enjoyed that. If you did, hey, feel free to share it with somebody that you know. You take care, and remember, always know what you build and share what you know.